Hello friends, welcome to this session. Today we are going to study topic stress strain behavior under the unit number 1, simple stresses and strain. So to understand the stress and strain behavior, we have to conduct one test, tension test onto the steel member. There are different type of the material we can conduct a tension test. It may be a mild steel, it may be a tar steel, it may be a aluminum. So different type of the material we can conduct the tension test. So today we have taken the example, we have conducted, suppose we have conducted the test on mild steel. At that time, how that steel it is behave after performing the tension test onto the mild steel. So first of all, we should know the stress. Already we have studied the stresses, strains. So again, stress is divided into two parts or two types. One is a nominal stress and another is the true stress. So that both of these terms we will try to understand in this particular topic. So first of all, nominal stress means whatever our normal or simple stress is there, that same definition is there. Load divided by the original cross section area is called as a stress, or it is called as a nominal stress. So, or simply we can say that stress. And strain we have defined, or we can calculate the strain by obtaining the value of extensometer reading. So we already discussed that extension after application of the pushing or pulling type of the force. So extensometer reading is required and divided by the gauge length. Gauge length means the original length of the bar, and by that we can calculate the strain. So extensometer means the change in length divided by original length means the gauge length. So following are the some of the silent features or silent points it is observed in the stress strain curve. So after performing the tension test onto the mild steel, so these are the some of the important points are there that we will study by using this stress strain curve. So you can see this particular figure, it is we will get after performing the tension test onto the mild steel bar. So first of all, very first term is there in this particular graph. You can see on the x-axis there is a strain, means extensometer reading is there on the x-axis, and there is a loading gauge, or there is a stress we have to take on to the y-axis. So stress is on y-axis and strain in x-axis. So this particular graph it is plotted after tension test onto the mild steel. So first term is limit of proportionality. So limiting, it is a capital A. So capital A it is shown in the figure also, capital A. So it is the limiting value of stress up to which stress is proportional to strain. So stress is proportional to strain. So 0 to A, this particular region, it is a limit of proportionality. It is a straight inclined portion is there. So up to A, that particular region it is called as a limit of proportionality. After that, elastic limit. This is the limiting value of stress up to which if material is stress and then release, so strain disappears completely. Means whenever that stress is applied to the material, and beyond that limit of proportionality, if you unload it or if you release the stress, then also uh, strain disappears and again regain its original shape, original length of the member. So that particular limit or that particular point it is called as the elastic limit. So that elastic limit point is certain beyond the limit of proportionality. So this point is slightly beyond the limit of proportionality. So next, upper yield point. So capital B, you can see this capital B point is their upward yield point. This is a stress at which the load start reducing. So at this particular value the load starts reducing, still the extension increases, and this phenomenon is also called as a yielding of material. At this stage the strain is about 0.125% and stress is about 250 MPa. So this particular B point here, it is load start just reduce, but still the extension is increases. So this particular point is the yielding point or yield point. So After that, ultimate stress, capital D. This is the maximum stress the material can resist. So ultimate means the maximum stress of any particular in the tension test material. If it is carry that particular stress, it is called as ultimate stress. So in this particular figure, so capital D you can see here. So the graph is at the highest point at D. So this is the ultimate stress or maximum stress that particular material can carry. So ultimate stress is for the mild steel normally 370 to 400 MPa, and at this stage the cross sectional area of particular section starts reducing very fast. This is important that that particular point the cross sectional area start reducing of this cross sectional area. So that phenomenon it is called as a neck formation, and after this stage the load resisted and hence the stress develop start reducing. So this is the maximum stress develop. So after that the load stress is decreasing after that. So after that the breaking point, so you can see the capital E is the breaking point which is a far below of the ultimate stress. So again still the extension is progress or increases, and for some time uh, there is a breaking point is there. So the stress at which finally the specimen fails, it is called as a breaking point, and at the breaking point the strain is about 20 to 25%. So breaking point is below of the ultimate stress. So you can see this ultimate stress capital D is at the highest point and breaking stress is somewhat below of the D, and somewhat lower value of the stress is there of the breaking point. Next, so this is a behavior, stress and behavior we studied about only the mild steel bar. So this particular graph we will get only for the mild steel bar. So in that there is a clear cut yielding point is there, upper yield capital B, lower yield capital C point is there, ultimate stress is there. So this is a behavior of the mild steel bar only. After that, this is the figure of stress strain relation in aluminum and high strength steel. So in this elastic metal there is a no clear cut yield point. The necking take place at ultimate stress, and eventually the breaking point is lower than the ultimate point. So you can see there is a no clear cut yield point is there. So there is a breaking, it is lower than the ultimate point. So the stress P, suppose if you take the stress P at which the unloading is made, there will be a 0.2% of permanent strain. If you take the stress P and there is unloading is made, and if you will get the permanent stress 0.2%, that particular point if you join by stress and that 0.2% strain, that particular point onto the graph, it is called as the yield point. You can take this F point we will get, this is the yield point. So this known as 0.2% proof stress, and this point is treated as a yield point for all the practical purpose. Understood? This particular yield point how will get the stress P at which there is a 0.2% of the permanent set or there is a strain 0.2%. So this particular dotted line is parallel to the proportional limit. So this particular inclined proportional limit and this particular line is parallel to the proportional limit. Only we have to take the 0.2% of proof stress, and if you draw the line parallel to this proportional limit, you can intersect this line at F, and this F point we can consider is a yield point for the all the practical purpose. So for the aluminum high strength steel, still there is a no yield point, so you can take the yield point like this 0.2% of proof stress. Again this is for the brittle material, again there is a no yielding point. There is no appreciable change in the rate of strain. There is a no yield point, means there is a no necking takes place, means there is a no reduction of the cross sectional taken place. So ultimate point and breaking point are one and same. So here is only one point is that ultimate stress and breaking point, or ultimate point and breaking point is same. So that is not there in the mild steel. There is ultimate point is the maximum stress and breaking point is somewhat lower than the maximum, and the strain at failure is very small. So it is only for the brittle material. So for example the cast iron is the material. If you conduct the test, you will get that ultimate point and breaking point same after application, after performing the tension test onto the that brittle material. So again nominal stress, you can see the nominal stress means load divided by original cross sectional area. So means whatever the simple stress we already studied or calculated, so nominal stress is same way, load divided by original cross sectional area. But there is a true stress is the load divided by actual cross sectional area. So the up to the ultimate stress, the stress strain curve is same for nominal as well as true. But at this particular point, there is a cross sectional area is reducing. And further calculating the true stress, we have to take the actual cross sectional area, means the reduced cross sectional area. Because of that, our stress value is goes on increasing, continuously increasing. That's why this dotted line you can see the true stress, because of we have taken only actual cross sectional area for calculating of the stress. Here we have taken only original cross section. That's why that ultimate stress value again decreases, and at particular point there is a breaking, it is taken place. Percentage elongation. So percentage elongation and percentage reduction in area are the two terms used for the measurement of ductility of any particular steel bar or steel member. So if you define this term, it is defined as the ratio of final extension at rupture to the original length express. So it is very simple. You can form this particular formula. Percentage elongation means in the longitudinal direction you can calculate. So L dash minus L. Here it is L is the original length and L dash is the length at rupture, means there is a change in length at rupture. So if you take the difference between length in rupture and original length, you will get the final extension, or there is a change in length divided by original length. If you want to finding out in percentage, multiply by 100. Same way you can calculate the percentage reduction in area. So again there is a ratio of maximum changes in the cross sectional area. In the elongation, the changes we have taken in the longitudinal direction, and in the for finding out the reduction in area, so changes is in cross sectional area we have to take to the original cross sectional area. So percentage reduction means original area A minus reduced cross sectional area A dash divided by A. So there is a change in cross sectional area divided by original cross sectional area, multiply by 100, we will get the percentage reduction in area. So after application of the tension test onto the any member, so there is a change in the elongation or extension taken place, you can calculate the percentage elongation, and at the same time there is a reduction in the area after tension test at the rupture point. So that reduction in the area also you can calculate, that is a change in area divided by original cross section area. So for the today, that's it. Thank you very much.